Okay, so welcome to today's class where we're going to be continuing our study on the cardinality of sets. Okay, so let's just take a few minutes to recap where we are at. So we're basically interested in finding out, at least for now, when two sets have the same size. Okay, so that's our main question. Um, when do two sets have the same size, right? And there are a couple different mathematical notions of what it means for a set to have a size. The one we are using is the notion of the cardinality or the cardinal numbers. And this idea basically is built upon bijections. Okay, so we do this using bijections. Oh, bijective function. Okay, so we say two sets A and B have the same cardinality, or they are equivalent if there's a bijective function between them. A and B are equivalent if there exists, so the symbol means there exists, f, which is a bijective function, between them. A goes B going to A, doesn't matter. And so now that basically allowed us to tell when two sets have the same size. So they have the same size if you could construct a bijective function from one into the other one. And we end up showing, so this is written as A is equivalent to B. And we showed that this idea of equivalent sets form an equivalence relation. Okay, so we show that this relation is an equivalent relation. So solar is an equivalence relation, right? So that means A is equivalent to A. If A is equivalent to B, then B is equivalent to A. And if A is equivalent to B and B is equivalent to C, then A and C are also equivalent. Okay, so, uh, so from that, we now have, okay, let me redraw this diagram that I did last time. So we have a set A, and so set, we have a set A, and now we could classify these sets in terms of their size or their cardinality. So over here, these are the finite sets. Okay, and over here, the infinite sets. And using that idea of equivalent sets, or finding bijections between them, we can now define rigorously what is meant by a finite set. So a set is finite if A is either equal to the empty set or A is equivalent to the set Jn. I remember what Jn is, so I'll define it up here. the set Jn is just the set of the first n natural numbers. So the natural numbers are 1, 2, 3, and you keep going. Jn just means you take the first n of these guys. So if you could find a bijective function between Jn for some value n and your set A, then we say that A is a finite set, okay? Or if it's equal to the empty set. And now for the infinite set, so we essentially know what all the finite sets are. For the infinite set, these could further be classified. So these could be the countably infinite sets or the denumerable sets. Denumerable, something called countably infinite. Right? And a set is said to be denumerable or countably infinite if instead of finding, so you see for the finite set, you just have to find a bijective function between A and n of the natural numbers. For the denumerable set, you need to find a bijective function from A and all of the natural numbers. Okay, so if A is equivalent, or if there's a bijective function between A and all of the natural numbers. So all of them, entire of them. Okay. So that's what a denumerable set is. And we could then say, or we will see in a bit, that these two guys, finite and denumerable, are what we call the countable sets. So countable means you are either finite or denumerable. Okay. And if you are not countable, then you are uncountable. Okay, so the uncountable sets go there. So this is the picture we have so far in our classification of the different types of sets. And so we know all the examples of the finite set. Just pick a set with a finite number of elements in it. But we came across some examples of denumerable sets, right? So by definition, remember, this relation is an equivalence relation. So every set is equivalent to itself. In other words, n is equivalent to n. The natural numbers is equivalent to itself because, of course, there's a bijective function from the natural numbers back into itself. That is the identity function. So that means, by definition, any set that is equivalent to the natural number is what we call a denumerable set. So the first denumerable set makes sense to be the natural numbers. So an example of a denumerable set, the natural numbers, because it's equivalent to the natural numbers. Every set is equivalent to itself. And we also saw that this set, if I take only the even natural numbers, I think we use this that's E to denote that is also denumerable, even though it is a strict subset of n. Instead of taking the natural numbers, you could take this set the negative of the natural numbers, right? Which is just the negative of it. This is also the denumerable set. So these are the examples we have so far. What we're going to do today is we're going to add a couple more examples to our denumerable set. But in order to add those examples, we need to exploit a particular fact, and that is if a set is denumerable, then it can be written in terms of a distinct sequence. So let me put that here. Right, so for today, we're going to talk about these distinct sequence and how exactly to use them. So a sequence is just a function, right? So a function has a domain, it has a codomain. So it's just a function where the domain is the natural numbers, right? And the idea is the sequence. So now we are used to calling the function f, and we are used to calling the input x, and the output, we are used to it being f of x. Okay, that is the typical function notation. The sequences, they do something slightly different. They don't call the function f. Okay, let me leave f there. The input, right? Since the domain of a sequence is the natural number, the domain for the function, instead of using x, they use the letter n, right? Because n is a natural number. So they use n. The name of the sequence, so the name of the function, they don't call it f, they call it x. And the output will be x of n, right? Or more commonly written as simply x sub n. Okay, so x sub n. So this is the notation for a sequence. Okay, so for example, if you have this sequence, let's say this sequence x, right? So that's the name of the sequence. It's a sequence, so by definition, the domain is in natural numbers and it's mapping into the real numbers. And let's just say it's given by defined by x and is equal to 1 on n. All right, so here's n and here's x of n. So when n is 1, it's 1 over 1, so this is 1. When n is 2, the sequence is doing 1 over n, so this will be a half. When n is 3, the sequence is 1/3, right? And you get the idea. And this is n, the sequence is 1 over n. Okay, so the sequence is this mapping, right? And of course, this guy here, this is x1, this is what we will call x2, this is x3, this is xn. So that's the notation with respect to sequences. Now, why are sequences important in our study of the cardinality of sets? It turns out if a set is denumerable, it can be written in terms of a distinct sequence. So by distinct sequence, I mean that the terms are all different. So let me give you a next example of a sequence, yn. So what about this sequence? It goes 1, minus 1, 1, minus 1, and so on. Okay, so notice that these terms are not all distinct or different. Okay, the terms are being repeated. So a distinct sequence means all terms are different. Okay, so let's go back into the slides now. Right, so over here. Yeah, so a sequence is simply a function with domain, the natural numbers. Okay, so this is what we just went through. Yeah, so the terms of a sequence need not be distinct. So the terms, the output may not be different. And they're saying here the range of a sequence may be finite or infinite. The range of a sequence is simply those numbers in the sequence. sequence, the output. So, for example, um, this sequence here, the range. So how many numbers are in the range of the sequence? So the range is infinite. Uh, right? There are infinite numbers in this range. However, in the sequence yn, the range is finite. The range is just a list of all the different outputs. Why is the range finite? Because the range is either 1 or -1. In the example xn, the range is infinite because it could be any number of the form 1 over n, right? And that's infinitely many. Okay, so they're saying that the sequence may be, the range may be finite or infinite. Uh, yeah, so you'll read through this. So this is where they're saying that for a denumerable set A, its elements can be arranged in a sequence of distinct terms. So if you have a set that has a bijection between the natural numbers and itself, then what you could do is you could list all the elements in that set in this way. Okay. And what is so special about this list? Two things. If A is a denumerable set, it means its elements can be listed or arranged in a distinct sequence. So it means each one of these x's are different. There are no repeats. And every element of A appears somewhere on this list. So this is the idea of what it means for a set to be countable. Countable essentially means you could write a list of it. You could list it out, right? Starting with the first one, the second one, the third one, and so on. Yes, the list will be infinitely long, right? This list keeps going and going. But the idea of countable means that if the set A is indeed countable, every element of A appears only once somewhere in this list. Okay, so let me write that down for you. Okay. So if A is denumerable, right? So that means there's a bijection function between A and B, natural numbers. Then the elements of A can be written as a distinct sequence. That means A can be written in this way, where each xi is different, right? There are no repeat. Different. And every element of A appears somewhere on this list. Okay, so that's the idea of sequences with respect to denumerable set. So we're now going to exploit this fact by showing that the denumerable sets are essentially the smallest of the infinite set. Okay, so before that, we have a couple of results. If B is a countable set, and A is a subset of B, then A should also be countable. So what this theorem and this corollary is, it's an extension of a previous result we stated for the finite set. So let me scroll all the way back and show you that. Yeah. So it's this one we did on slide 10 that said every subset of a finite set is finite, every superset of an infinite set is infinite, and if A and B are finite set, then the union and intersection is finite. So the idea is, you see the word finite, we want to replace that now by countable, because countable means finite or denumerable. Okay, so the extension of it is given by these results. So if B is now countable and A is a subset of B, then A is countable. Or every subset of a countable set is also countable. And the corollaries are given by every infinite subset of a denumerable set is denumerable. So countable means either finite or denumerable. So they are saying if B is a subset of A, okay, and A is countably infinite or denumerable, and B is infinite, then B has to also be denumerable. And if A and B are countable sets, then their intersection is also countable. And if we take the contrapositive of this theorem, we get this last one here, which is every superset of an uncountable set is uncountable. So if you have an uncountable set and you take a set bigger than it that contains it, that set is also uncountable. Right? The proof is left for you to look at. Yeah, so the first main result now is that every infinite set has inside of it a denumerable set, right? So we are trying to classify the different sizes of infinities. We know that a set now could either be finite or infinite. Right, let me go back to this little chart I have here. Right, we know that a set is either finite or infinite. What this result is saying is that if your set is infinite, then inside of it, you can always find one of these sets, the denumerable set. So inside every infinite set is a denumerable set. Okay, so the construction is straightforward, but it's hiding a lot of things behind it. But I'll give you a little quick idea of it. Set the job, just like that. Right. So this is your set A, and A is infinite. Okay. What we're saying is that inside A, if A is infinite, so I didn't tell you what type of infinite that is, but inside of A is a denumerable set. Okay, and the construction is very easy. What we're going to do to construct this denumerable set is, since A is infinite, we're going to take any element of A, call him A1. Okay, then we're going to take another element of A different from A1. Okay, and the whole argument is that how is there another element of A different from A1? Well, if A is infinite and you take A1 and you remove it from A, then A is still infinite, right? Otherwise, A would have been finite. So the idea is, if you choose any point of A, A1, there are infinitely many points remaining. So choose another one that is different. Call him A2. And now we repeat that. Then we remove A1 and A2 from the set A. How many points are remaining? Still infinite. So there exists another point, A3, different from A1 and A2. And we're going to continue in this way. Okay, so that's how we make this denumerable set. Right, very straightforward construction. Okay, so let's go through the proof of it. So every infinite set has a denumerable set. So let A be an infinite set. We construct a denumerable set of A as follows. So exactly what I said there in that picture, we now need to write it down rigorously. So let A1 be any element of A. Okay. Since A is infinite, A cannot be equal to the set containing only A1, right? So if A is not equal to the set containing A1 alone, then that must mean that there exists another element A2 in A different from A1, right? Such that A2 is in A. Now again, since A is infinite, A cannot be equal to the set of A1 and A2. If A is not equal to the set containing A1 and A2, that means there must exist another element A3 different from A1 and A2, such that A3 is in A. So continuing in this way, we obtain a subset B, and B contains these A1, A2, A3, and so on. Now, by construction, B is obviously a subset of A, because where are the elements of B coming from? They are coming from elements in A. So by construction, B is inside of A. Now we need to just argue, why is B denumerable? Well, denumerable means there's a bijective function between the natural numbers and B, right? So this bijective function is very easy. When you give me 1, I give you A1. When you give me 2, I give you A2. When you give me A3, 3, I give you A3. When you give me N, I give you AN. So now we could write down what exactly this function is. So I'm going to call this function f, and it's going from the natural numbers to b, defined by f of n is simply an. So any natural number you give me n, 100, I'm going to give you a 100. Okay, so this function is clearly a bijective function, right? Because every element of b is assigned a natural number n, so it's surjective, and no two elements of B are the same. Notice that. Why are no two elements of B the same? Because that is how B was constructed. Remember, in the construction, I always took my next A to be different from all the A's I had previously. Okay, so by construction, uh, no element in B is repeated. Okay, so therefore B is denumerable. So a very important consequence of this result is that from this theorem, it shows that the denumerable sets are the smallest of the infinite sets. So what does it mean to be the smallest of all infinite sets? It means if you have any infinite set, inside all of them is a set of this size, the denumerable set. Okay, so they are the smallest of the infinity. Okay, so something else we'll need for what comes later on. And for the proof of this, you could see any of the reference texts. The proof is a bit involved. Okay. This now gives us another way to show that a set is countable. It turns out if a set if a set is countable, so that means it's either finite or denumerable. If a set is countable, it means it is either finite or denumerable. That means there is either a bijection between the set and this guy Jn, or there's a bijection between the set and F. So it turns out that if a set is countable, we don't exactly need a bijection. We could we could we could show it's countable with either just an injective function or just a surjective function. We don't need the full bijective function if we are dealing with the countable set, so long as we choose our domain or codomain very specifically. So what do I mean by that? Okay, so in this theorem, let A be a non-empty set. Of course, if A is empty, then it's finite. We find the empty set is finite. So we're just saying, okay, suppose A is non-empty, then the following conditions are equivalent. So equivalent means each one of this implies the other. So when any one is true, all of them are true. So A is countable. Another way of saying A is countable is that there exists an injective function. So notice we don't need the full bijective. Injective is enough, but the restriction is the injective function must go from the set A into N. So notice where the natural numbers appear here. It appears as the codomain. So if you are using injective functions to show something is countable, you need to put the natural numbers as the codomain. If instead it is more convenient for you to put the natural numbers as the domain, then you need to show that function is not injective. You need to show that function is surjective. So A is countable means there is an surjective function from the natural numbers onto A. Okay, so make sure you remember which one. Injective uses the natural numbers as the codomain. Surjective uses it as the domain. In fact, you see the natural numbers over here. You don't even need to use the natural number because we know that that equivalence of set is an equivalence relation. We can substitute for the natural numbers any other denumerable set that we have. So in the statement of this theorem, it still remains true if we replace, so here should be the fancy N, natural numbers. If we replace the natural numbers by any other denumerable set. So now what we're going to do is we are going to start constructing denumerable sets and using this theorem to get more, right? So the theorem tells us that when a set is countable, okay? Countable means infinite or denumerable. So if I know a set is countable, so what I'm saying is, if I know a set is countable, and I know it is not finite, then it must be, of course, denumerable. So that is our strategy now. We're going to construct denumerable sets, so prove certain sets are denumerable by either using injective or surjective functions from those sets and the natural numbers, either as the domain or codomain. So let's see how to do that. So the first one is n cross n is countable. Okay, so I have to explain this one a little bit. Okay, so we know n is denumerable. So therefore it is countable, right? It is countable. Countable means either denumerable or finite. Of course, n is not finite, so it must be denumerable. What we're going to show is that not only is n denumerable, n cross n is also denumerable. Right? And now we need to know what this notation means, n cross n. So remember Cartesian product. So n cross n is just the set of all pairs of numbers n m such that n and m are natural numbers. Okay, for example, so think coordinates, xy coordinates. But the restriction is that the coordinate numbers could only be natural numbers. So for example, 1, 7, um, 2, 9, 12, 100. Right? So all of these belong to n cross n. Pi 1 does not belong to n cross n. Okay, because pi is not a natural number. So that is what n cross n is. Okay, so what is the strategy here? The strategy in this one is we're going to construct an injective function. The strategy, I'll put here the idea, is you want to make an injective function, right? So if I'm using the injective function, let me go back to the slide. If I'm using the injective one in this term, so look, the injective one needs to go from the set into the natural numbers, okay? From the set into the natural numbers. So the set A in this case is n cross n. So we want to make an injective function f from the set that we are looking at. In this case, it's n cross n into the natural numbers. Okay. So whatever function we come up with, we then need to prove that that function is injective. So here's the clever construction of this function. Yeah. So the domain of f is n cross n, meaning it takes in a pair of natural numbers. Okay, so the domain, it takes in n, m, pair of natural numbers. The output has to be a natural number. But I can't just put any natural number here. For example, I can't just say let the output, I don't know, be, let's just say n. Because if I do that, watch what happens. If I do 7, 10, the output according to this recipe is 7, right? The first one. What if I do 7, 9? What would the output be? Still 7. So this function, nm mapping onto n, is not injective. It's not one-to-one. Okay? So we can't just put any output. We need to put an output in such a way that the resulting function is injective, one-to-one. So you could sit and think about what possible way you could do it. There are many ways you could do this. A very clever way is to put the output being 2 to the n, 3 to the m. Okay, let me just make sure that's what they didn't do m and n. They did n and m. Yeah, so m and n. Okay, so let me keep it like that. Okay, so I just swap in the m and the n to make it consistent with the nodes. Okay. I just switching them over. Let's do m first and then n. It doesn't matter. M first and then n. Okay, so for example, if I now throw in 1, 3. Let's just say, for example, the output is 2 to the 1 multiplied by 3 to the 3, which is 2 by 27, right? Whatever that is, you look it up. If I do 1, 1, then the output is 2 to the 1 by 3 to the 1, right? So the output is a natural number. Okay, so now I have made a function that takes in 2 natural numbers and gives me 1 natural number. Now I need to then prove that this function really is injective. Okay, so let's see, why is this function injective? So we're going to define a function f from n cross n into n by f of mn equal 2 to the m, 3 to the n. And I put over here that we could use any prime numbers. So I'll explain after why we could use any prime numbers. Why do we take 2 and 3? So we show that f is injective. Of course, you all know how to show a function is injective. You take 2 elements in the domain. So m1, n1, m2, n2, 2 elements in the domain, and you then say, suppose f of x equal f of y, you need to show x equals y. So suppose f of m1, n1 equal f of m2, n2. I need to show m1, n1 is equal to m2, n2. So by definition, f of m1, n1 is 2 to the m1, 3 to the n1, and by definition, f of m2, n2 is this one. Okay, and now you just use your rule of indices. So take this 2 to the m2 over to the left, and 3 to the n1, take it over to the right, and use your rule of indices, and you can arrive at this one. So if you have 2 to some power equal to 3 to some power, then powers must both be 0. Okay, the only way this can happen is if this thing is 0. So you get m1 minus m2 equals 0. In other words, m1 equals m2 and n1 equals m2. So the output are the same. So this shows f is injective. So now we know that n cross n is countable. Since n cross n is infinite, it is denumerable. Right? So in our list, where am I going to put n cross n? We show that n cross n is countable, but it's not finite, so it must be here. N cross n. Okay? Yeah, so the reason why we use prime numbers here, right? We could use can use any prime numbers. Okay. Is because of with the natural numbers, we have unique prime factorization. Um, what's that called? Fundamental term of arithmetic. These numbers have a unique prime factorization. That basically means that you could take any natural number. I'll give you an example. Like what's a good one? Like 30. And you could break down any natural number into the product of prime numbers. So 30 is 3 by 10. So 3 is a prime, but 10 is not. So this is 3 by 10 is 5 by 2. Right? So this is unique. So if we have like 2 prime numbers, so let's say 5 to some power x equal 11 to some power y, then this is only true if x is equal to 0 and y is equal to 0, because then in that case you get anything to the power of 0 is 1. Okay. So that's the idea um, in which this proof works on. Okay, so we have n cross n is countable, and so I guess what we do next time is we'll show because we don't have time to go through this one today, is we're now going to then exploit the fact that n cross n is countable to show that the Cartesian product of two countable sets is countable. So if A and B are countable sets, then their Cartesian product A cross B is also countable. Okay, are there any questions? No questions? Okay, so if no questions, we'll stop there today. Okay, great. So if any of your friends missed today's class, I will put up the link to the recording um later today. Okay, so I will see you all on Wednesday then.